Hi guys, I'm going to start the live stream right now. First thing I want to talk about is Wednesday. I'm going to have class, whether it's at my house or whether it's here. I'm streaming something, all right? So I'll communicate with you guys, but about what it is. But just remember, like, if don't, it's class is going to happen whether you're here or not. So don't stress about coming to class if the weather's crazy or if it's just take care of yourself. Make sure you get snacks. That's what I'm worried about right now, right? Making sure we got water and snackies. And but I'll communicate class accordingly. And so now you know. Moving on to new material. I cannot emphasize this enough. Definitions, what are things and how variables affect other variables is what I'm going to emphasize on the test. I'm never going to ask you to solve for X because in the real world, we usually don't solve for X. But how different variables affect other variables. Like, for instance, you know that if you train consistently, you're going to get stronger. And if you incorporate, diet and exercise, you're going to get healthier. Like just how different variables affect other variables. So what we're going to talk about today is impulse and momentum, which is simply just rearranging Newton's second law. That's all it is. F is equal to ma. Well, technically, what is A? Delta V over T, change in velocity over time. So when you separate it into those categories, you could do a little cross multiplication and you get the impulse momentum equation. But that all that is just rearranging Newton's second law. You do this every day in your car. Your car has mass, hopefully you in it, and bless you, and you want to change its velocity. You're at a stop sign or a red light, and you want the mass of that vehicle, that system, to get faster and faster and faster. So what affects that? The unbalanced force, you're pressing on your gas pedal, and how long do you press on the gas pedal? Force and time. If you need to slam on your brake to change your velocity of the mass of your car in a small amount of time, you better apply large force. Okay? So impulse, momentum. I think impulse is probably derived like how we use it in pop culture. Like that was an impulse decision. Like probably it was a large emotional response and you didn't give a lot of time in it. So it was highly impulsive. Okay. So momentum is simply just mass in motion. Mass in motion. And what affects it is force and time. But it's not any separate equation. It just, look, there it is. It just derived from F is equal to ma. Okay. So just know how these things affect each other. If I were to load up the car with a lot of heavy stuff and as many people as possible, if I increase the mass, it's going to take either more force or a lot more time to change my momentum. Remember from a couple weeks ago, the equal sign is just proportionality. As the left side goes up, the right side has to go up. If it's on opposite sides of the equal sign, things on the same side of the equal sign are inversely proportional. Meaning, if I supply a certain amount of force over a certain amount of time, if I lessen the mass of the system, hey, everybody get out of the car, right? Lessen the mass, well, then my velocity is going to change fast. As this goes down, this goes up, given the same net. That's what you're going to have to know in the test. Just what is it, and how do different factors affect each other? This increases, that increases. This decreases, that increases. This increases, that decreases. It's just the variations of Newton's second law. Work, power, and energy. In grad school, you're going to have to calculate a lot of this. MGH, mass relative equations, 1/2 mv squared, and all that stuff. For our class, it's important to just, again, know what these concepts are and how we're going to apply them to muscles influencing motion through contraction. Okay? Energy is the capacity to do work, the potential to do work, right? And I know physiologically, I'm not a physiologist, but that's where we have these stored energy batteries, ATP, and that could be transferred into doing usable work. Okay. I think the key thing here is that work, power, and energy, because someone asked me this question the other day, I forgot which class, it was a brilliant question. If I'm running, I think it was a 310. If I'm running on a treadmill, right, so I'm not moving, how am I breaking a sweat? Because there's no mechanical work. And I'm like, well, that's because we're not thinking of it where you're thinking of it traditionally. You're thinking of why I'm not moving relative to the whole room, but I'm 100% moving relative to that belt. That belt is trying to sling me over here. And if I don't want that to happen, I got to run this way to keep me on the same space. It's no different than swimming in one of those plumes that is providing a resistance, right? Or the river. I'm swimming upstream with a current. The current wants to make me flow down the river. So even though I'm swimming upstream and I'm not moving, I'm working in order to keep me in that same position. No one would say, if I hold my arms out, eventually I'm going to get tired. Maybe you don't see any mechanical work, but that doesn't mean my muscles aren't doing a job, right? Physiologically, they're working to keep me in this position because gravity is trying to move me to that position. Okay? So work, power, and energy. We have the capacity to do work. Work, as we remember in 310, is what your muscles do above rest. Very important. Your muscles technically are working right now, but they can maintain that all day. My body has a metabolism, a resting basal metabolism, you guys heard in physiology, while I'm watching Game of Thrones with my wife or whatever. But I can do that all day. What we consider working, my son's 17, when he becomes 18, got to get a job. He needs to do something beyond playing video games. Something beyond, what are playing video games your job? No disrespect to video games. I'm saying that it has to be above and beyond rest for it to count as work. You cannot maintain a level of above rest activity forever. You're eventually going to need a rest. You're going to need a break. Okay? So in regard to our muscles, that's why we refer to work as contractions or contractions as work. Muscle contractions done by muscle agonists, the workers, are doing a job above rest because they can't maintain it all day. Your erector spinae have worked themselves up to being able to maintain your neck position for hours at a time. You weren't born like that. You had to build up that endurance. And even then, at the end of the day, man, your neck might be tight, start getting a little tension headache up there, so you got to lay down and rest. Just because muscles and our groups are shortening and lengthening does not mean they are contracting. Just because muscles are shortening and lengthening doesn't mean they are working above rest. Does that make sense? The analogy I gave in 310, love this analogy, is blood pressure. I don't know if anybody remembers the blood pressure analogy. Atmospheric pressure, 760, true? 760 millimeters of mercury at sea level. Our venous pressure is a fraction of that. Like you prick yourself, you don't squirt out, right? The veins, like the little capillaries, it's just a slow leak. So if there's more pressure outside than inside, when you prick yourself, you should implode. The trick is that our arterial venous capillary pressure, 120/80, 40, 10, is on top of 760. Like 760 is atmospheric pressure for everything. So it's almost like we subtract 760 from everything, and we're only talking about the extra. We're only talking about the lagniappe. My venous pressure is 40 millimeters of mercury after I subtracted the 760, in other words. Does that make sense? So it's very similar to how our muscles work. Our muscles pull all the time, true, but there's a basal level, a metabolic level about which they pull. That is not what we consider working. That's watching television on a sofa or a couch. Working is doing something above rest, doing a job above rest. That's what we term contraction. Okay? So when our muscles work, they're doing a job. When you work, you do a job. We're good so far? All right? Power is simply how much time did it take you to do the work? So I love doing standard comparisons. You and I both weigh the same, and we both run the same displacement, 40 yards. If we weigh the same and we ran the same, then we can create a control experiment to say, well, if you did it in less time, you can inferently be more powerful. There has to be an element of time. Oh, you got your work done really quick. You would, in layman's terms, would be you were more powerful. We get into inferences with these things with examples like the 40-yard dash. I've mentioned this before, where everybody's displacing the same, but not everybody weighs the same. So since everybody's displacing the same, variations of time infers variations in speed. In other words, when you're doing the 100 meters in the Olympics, it's not relative to body weight. It's just who displaced in the least amount of time, right? So we've already set the precedent that we know more physics than we give ourselves credit for. Because when the conditions are the same, the displacement, the top part is the same, variations in time infer variations in speed. We both run 40 yards, but I did it in less time. I had to be going faster. We run 40 yards. I did it in more time. I had to be going slower. It's the same inference with power. So what do I mean by that? And I give some examples, all right? We'll talk about these things. But it's the same thing for power. When somebody is doing like power lifting or power lifts, it's not that you're necessarily measuring power, it's inferred because there's an element of speed that it takes in order to move that weight in a small time. What I mean by that is, like for the clean, if you went too slow, would you have time to pull yourself under the bar and catch it? You know what I mean? Like there is a window of time in order to catch yourself under the bar. So the power is kind of inferred through that window of time, okay? In layman's terms, all power is how much time it takes you to do the work. But power lifting isn't necessarily them calculating the time. It's just, did you complete the lift? And the inference of power is, did you have enough time to get up onto that bar or jerk, get up on, right? That sounds like some kind of song. Get up onto that bar. So all I'm trying to say is that we use mechanical terms and definitions fast and loose, and that's okay. I'm not trying to rechange how we use these things. But what I am trying to do is explain the inference of why. You know, there's a time component, and when there's a time component, that's what makes things, how much time did it take you to do the work. So in these examples, you know, someone could technically, you could have two people run a 40, and because of one person's mass or weight being greater, but yet they run the same time, they could be more powerful. But in a 40-yard dash, who cares? It's just who displaced in less time. Like, that's not a variable for that kind of measure, right? Anybody a football nerd like me and like watch the NFL Combine? Like every now and then you'll see like big humans running some and you're just like, the most powerful, they don't do this anymore, I guess, because of injury, but I don't know, it seemed to be pretty safe when I was in school. I try to give analogies for some of these things I'm trying to babble about. But for senior day, when I was an athletic trainer with working with the football team, they'd had a tradition when Coach Stokely was here, and the seniors on their last practice get to pick any of the underclassmen, and we would all make like a gauntlet, and the underclassmen had to hold a padding, but they couldn't see them coming. And that senior got a running start and just, pow, comes up. Offensive linemen usually wouldn't lay big licks because they were big people, but they ran slow. The defensive backs usually wouldn't knock the tar out of people. They were fast, but they usually small. You know who got in the best licks? Powerful linebackers, fullbacks. People that were kind of in the middle. I had a little bit of both. They were strong and fast. They weren't the fastest of the fast, and they weren't the biggest of the big. Something in the middle. And that's what's elegant about power. Power lives in the middle. Why? Check this out. This is in your third PowerPoint that I posted on Unit 1. Look at this graph. Power is a combination of force and speed. I think of it like this. It's like you don't want to take a shower that's too hot. You don't want to take one that's too cold. You just want it warm, right in the middle. If something's too heavy, you're not going to get it to move very fast. If something's too light, you get to move fast, but it's not very heavy. So where does optimal power live? Somewhere in the middle, because you have a little bit of both. So in that analogy, fullbacks, linebackers have a little bit of both. They're faster than the linemen, but they're bigger than the defensive backs. So they typically are more powerful. That doesn't mean no one else has power. I'm saying in terms of optimal power, you got to have a little bit of both, some force and some speed that combine for optimal power. Think about it, guys. A glacier has a ton of momentum because that has a lot of mass, right? But it's going so slow, could it break an egg? No. You know, if a car is moving very slow, it can't crack an egg. So that combination of force and speed is where power lay. Right? And that's going to come into eventually looking at the different attraction types, right? So in other words, something's moving very, very fast, but as here's a good analogy. If I gradually increase the dumbbell in my hands, like let's say I'm unloaded just the mass of my arm, I can flex it as fast as I can. But if I put a 2-pound weight, 5-pound weight, 10-pound weight, 15-pound weight, if I make the load get greater and greater and greater, I can't flex my elbow as fast until eventually I have a load where like I'm barely moving it at all. So optimal power lies in between max speed and max force. Optimal power lies somewhere in the middle. All right. All right, you guys. Trigonometry and biomechanics. I get it. I get it. I get it. I get it. I know. I know. Give me a chance. I am not going to ask you to calculate anything. I'm just going to ask you to see some logical things that if I do my job, you will be able to see and understand. When someone sprains an ankle or they have swelling in their leg, what do we usually tell them to do? Or, protection, rest, ice compression, elevation. But we will have them elevated, right? Get above their heart, help with the swelling. Elevating it at 90 degrees is probably optimal. But the reason people don't do that is because it hurts. Like when you have 90 degrees, like pain is a limiting factor to that. So in other words, at 90 degrees, you're getting all of gravity, but you're also getting a lot of discomfort. So typically we'll do it at an angle. We'll do it at an angle. And what's awesome about angles is that angles are inversely proportional to their components. This is the key to trigonometry. Let me show you what I mean. In our normal world, we have linear thinking brains. 2, 4, 8, 16. Like we have linear thinking brains. If I work for an hour, I get this amount of money. And if I work for 2 hours, I get double that amount of money. That's how our brains work. What our brains are not good at is curvilinear thinking, like things that are like squared and cubed. Things like if I work 1 hour, I get this, but if I work 2 hours, I get more. And if I work 3 hours, I get, like, our brains don't think curvilinearly, our brains think linearly. And that's why I think trigonometry messes with us, is because trigonometry is non-proportionality because of that square, right? A squared plus b squared is equal to c squared. So let me try to show you what I'm talking about. Check this out. Pythagorean theorem, right? Okay. I'm not going to ask us to solve anything. Don't care. But those squares are very important. Those squares are very important because what those squares tell us is that we cannot say on a right triangle, and I'll explain why that's a right triangle. What we can't say is the A component and the B component equals the C component. That's how our brains want to think. Our brains want to say that A, let's say that's a distance or displacement. Like if I walk so many steps here and I add that to so many steps here, it should equal so many steps there. That's not how it works. I'll give you an example. I'm going to walk to this chair. I'm trying to give this example for the stream to see. Dr. Madsen gave us this example in class. All right, I'm going to walk to the chair. I have options. I can either walk straight to the chair in 2 steps. That would be like the C. Or I could walk around. I could go the long way. Think of it like that. I can travel A first and then add my steps to B. going the long way will always be greater than going straight there. Does that make any kind of common sense? This plus this will always be greater than this. That's why we have to square it to make sense. So far, so bad? Okay. The sum totals of the component vectors will always be greater than the hypotenuse, is what I'm trying to say, unless we square it. Now, here's what the application of today's class is. If you guys have your calculators, and listen, I'm not going to ask you to use your calculators in the test. I'm showing you what I'm saying has truth to it so that you can say, ah, I see. Go to your phone and hit on the calculator. Make sure your screen locky thingy is offy. And when you rotate it on the side, you get some extra little buttons. You get some trig functions, sine, cosine, tangent. We're good? Okay. Let's say I have a basketball goal and it's laid down. There's the rim, okay? We know, I'm not the greatest artist in the world. I'm being humble. 10 feet to the rim, right? We know that when it's laying down before I raise it up, all of that 10 feet is in the across. There's no verticality to it. And I also know when I raise it up, all of that 10 feet is going to be in the vertical and none of it is going to be in the horizontal. What's interesting is as I raise it up, it's going to get less and less and less horizontal and more vertical. And that's because in trigonometry, the component sides are directly proportional to the angles that create the different sides. And you say, well, I remember hearing something about that in high school or college trigonometry, that it always involved a right triangle. Why does it always involve a right triangle? Because X, Y, and Z are always 90 degrees to each other. Any component has to be perpendicular. The verticality of that basketball goal has to be perpendicular to the verticality. The horizontal part has to be perpendicular to the vertical. We're just keeping it in 2 dimensions right now. Your normal human functioning brain wants it to be linear. In other words, as I go from 0 to 30 degrees, whatever distance I lose here should be exactly the same as what I gain here. And that's not how trigonometry works. And that's what I'm trying to emphasize today. Our brains want us to say 30 degrees, this has to be the same as that. And I'm going to show you that it's not, but I'm also trying to show you why, because of that squared part. First of all, I established why it can't be A plus B is equal to C, because A plus B will always be greater than C. So let's do some trigonometry to show you what I'm talking about. I raise the basketball goal from 0. Let's say I raised it. Yoink. I'm just eyeballing it here, guys. 35 degrees from the horizon. Not from the horizon, who cares? I angle it 35 degrees from the ground. All right? So here's the question. Sure, it's still 10 feet from there to there. The hypotenuse is still 10 feet, but I could say, well, how tall is the basketball goal now? How high is the basketball goal now? And thus, how long is the basketball goal? Well, I know it got shorter in the X, but it got taller in the Y. True? So So again, that's what trigonometry does. Trigonometry says, well, I have a y component. That basketball goal has a height, and I have an x component. That basketball goal has a length. I know it's 10 feet, but I don't know how much of that is across or how much of that is up yet. So we're going to do trig. Why don't I use meters? Because America, that's right. That's the correct answer. All right, guys, let's take out our calculators. I think this is really cool. When you put in, first of all, again, a review, you know that the sine function, whatever the heck that means, is just opposite side over hypotenuse. All that is a ratio. That's all it is. I'm going to teach you that when you see a decimal place, that's a percentage. How much of it is across? How much of it is up? That's all that decimal is. It's the percentage. If all of it was up, then it would be 100% in the y. If all of it is down, it'd be 100% in the across. That's why, like, if you put 90 sine, go ahead and put 90 sine. What number do you get? Yeah, because if the basketball was here, 100% of it would be in the y. These are decimals as percentiles. All right, here we go. Clear it. We're going to go 35 because I'm 35 degrees from the horizon, from the ground, and I'm going to hit sine. Now, you and I just see a bunch of numbers, but what I'm trying to get you to see is a percentage. That basketball goal is 57% of its length up. So what's 50% of its length? This times 10 feet. That's all it is. So you'd say, all right, well, what's the hypotenuse? 10, so 0.573 times 10 equals, it's 5.7 feet up. That's all that means. You remember the cross multiply, setting up that's all that means. How much of it is across? Well, since the x touches, remember guys, opposite side is like across the street. And adjacent side, like the adjacent house touches your yard, right? So the x component, if we clear out, we're going to go 35 cosine, we get a different percentage. Now look at that percentage, 81.9%. That should tell you that more of it is in the across than the up. The up is only 57%, right? So 82% of what? Times what? Times 10. The basketball goal is 8.19 feet across. Now again, some weird stuff happens with nonlinear concepts. How in the world can 8 feet across plus 5 feet up, that gives me more than 10 feet? Yeah, that's trigonometry. It's always going to be greater to take the long way than straight across. That's okay. We know that halfway would be 45 degrees, right? 45, each side would be equal components. So let's do the opposite. Instead of 10 degrees below, let's go 10 degrees up. I keep raising the basketball goal, and I raise it to 55 degrees from the horizon. There's my goal. Should make sense. I'm getting taller and taller and taller, and I'm getting less across as I raise it up. Check out these percent changes. Clear? We're going to go 55 sine. Now the y component is 82%. In other words, look at that shift in percentage, but yet I only moved the angle 20 degrees. A 20-degree change in angle created a huge difference. They basically flipped spots. You see what I'm saying? So if someone is elevating their leg, let's say this isn't a basketball goal. This is from athletic trainers. This is for my allied health professionals. Let's say this isn't a basketball goal anymore. Let's say this is a leg. That's a foot. And they're elevating their leg. What I'm trying to show you is, with angles, sides, and components, that if you can elevate your leg at 55 degrees, 90 degrees would be straight, and that comes with pain. At a 55-degree angle, not only do you not have as much pain, but you get 82% of the effects of gravity. That's what I'm trying to tell you. That's what I'm trying to show you. You get 82% of the up and down. 82% of the effects of gravity, and you're still 35 degrees away from hitting 90 degrees. Does that make any just practical sense? Again, guys, I'm not going to ask you to solve for the sine, the cosine, of the tangent of the inverse function. There's in-proportionality between angles and sides. Same with muscles. If a muscle has an angle, just because it changes angles a little bit doesn't mean its effects are going to change a little bit. You change an angle a little bit, and it affects the components a lot. Because these things are square. There's an amplification to these changes that are not linear. They are curvilinear. Little changes produce greater effects because of the square. So that being said, all of the things that you see here is trying to explain those concepts. That it's not A plus B is equal to C, they're all squared, because this plus this by itself will always be greater than this. That's why we have to square them. Okay? Pythagoras. It wasn't Pythagoras. It was a French dude, Descartes. He was, dude, this was before Fortnite, man. So he was like in his room and trying to describe the position of like a spider on his ceiling because he thought it was going to impress somebody. I guess you got to do what you got to do back in those days. And so he came up with a coordinate system and the Cartesian plane, heard of. And this Cartesian plane is great for linear thinking. Like, I go 2 spots, I go 2 spots, I go 4 spots, I go 4 spots. And so our application of this Cartesian plane can be used linearly when we're plotting things. What I'm trying to show you is that, remember in 310 how planes and axes, objects rotate about an axis, okay? Here is my axis, and as Ken rotates, his component length changes. All of his length is in the X. Now all of his length is in the Y. Now all of his length is in the negative X. Now all of his length is in the negative Y. And trigonometry shows us that as Ken's length changes, he gets taller and taller and taller in the up, while he gets shorter and shorter and shorter in the across. That is not linear. That is curvilinear. Little changes in angles create nonlinear changes in the components that I just showed you. A 20-degree change here literally flipped what was 81% to what's 81%. That makes sense? So that's what this stuff is. Trying to explain eventually how this happens. You have muscles that pull at angles. Immediately, as undergraduate biomechanics students, we should immediately say, oh, if it's pulling at an angle, that must mean it has components to its pull. Not all of this muscle's force, let's say the F is the muscle pull, not all of that pull is trying to move that bone, is what I'm trying to get to. There's a component that's perpendicular that has a rotary or moment component, but there's also a component that's linear, trying to keep this bone into the socket so that you don't have a bad day. The stability component of a muscle's pull and the rotaries component